Hello. The subject of this video is the very interesting paper called Toolformer, Language Models Can Teach Themselves to Use Tools. The problem that this paper talks about is very interesting, especially these days with the recent advancements in large language models and, the introduction of things such as ChatGPT plugins and basically the interactions between large language models and famous tools such as Wolfram Alpha that allow new possibilities and opportunities. So this paper is now very interesting to read. And it was published in February of 2023, so it's rather recent. Without further ado, let's dive in. The abstract starts by saying language models, specifically large language models, exhibit remarkable abilities to solve new tasks from just a few examples or textual instructions. The specific keywords related to these three lines are few-shot learning, zero-shot learning, and in-context learning or prompting. The intuition is pretty much like this. If you have a large language model, a model as big as, let's say, GPT-3, which has around 170 billion parameters, what happens is that when that model has seen enough text, has been trained in an unsupervised manner for a long time, what happens is that there is this emergent knowledge in it, meaning that if you provide it with certain, let's say, a few examples of what you want it to do, like, for example, read through this text and extract the number preceding a certain set of words or something like that. When you do that, it could easily take over and perform that task for you. So that's essentially what it means when we're talking about few-shot learning and zero-shot learning in this context. And basically, you could provide a prompt like that and feed it to the language model in addition to your input and basically expect it to perform it for you. This is related to one very other interesting paper called prefix tuning, which we have covered in this channel in one of the previous videos, and essentially this showcases the ability and the main key ability of large language models. The goal of this paper is to showcase that language models, specifically large language models, can teach themselves to use external tools via simple APIs and perform really nicely, which results in Toolformer, the model that they introduced. One thing that this model does is to decide which APIs to call, when to call those APIs, what arguments to pass, and how to best incorporate the results. They show these abilities in a QA system, a search engine, a translation system, and a calendar, resulting in improvements in performance in zero-shot settings across a variety of downstream tasks. So let's get started and see what they've done. The paper first starts by talking about the limitations of these large language models, specifically the fact that they are unable to access recent and up-to-date information, the related tendency to hallucinate. For example, you've seen this a lot with the reference generations in ChatGPT, difficulties in understanding low-resource languages, lack of mathematical skills, and things like that, and, for example, the unawareness of the progression of time. So they want to kind of give the language model the ability to interact and use with the other types of resources, such as search engines, in order to augment its functionalities. And to this end, they proposed a Toolformer model here, and one of the key components of this is that self-supervised learning and self-supervised setting is going to be used in teaching the system to use these APIs and these external tools, and therefore not requiring large amounts of human annotation. This figure provides an example of Toolformer's predictions. For example, the first one is a question answering system. The question is, who is the publisher of the New England Journal of Medicine? The system generates the tokens. The New England Journal of Medicine is a registered trademark of, etc. Here, it decides to use this functionality and do the question answering system and get the result, which is the Massachusetts Medical Society, and respond with the MMS. The other component of this is a calculator. Like, for example, it says out of 1,400 participants, 400, or in the parentheses, it decides to use the calculator. And, for example, it would be calculation of 400 divided by 1,400, and the result, which would be 0.29, represented as a percentage, results in 29% pass the text. The third component is a machine translation. The name derives from this term, the Spanish word for. In this case, it realizes it has to use a machine translation on this word and then results in the word turtle, so it puts the turtle here. And the last one is a search engine from Wikipedia. For example, it says the Brown Act is California's law, and in this case, it decides to use the wiki search and basically get the output of this, which is this component, and then use it in the context. That requires legislative bodies like city councils, etc. So this is essentially how Toolformer uses these types of external tools and incorporates their outputs in its generated stream of words. The other key novelty is that the language model has to still be general enough and understand when, how to use these tools and to use which tools. The idea is something like this. First, you have to provide a handful of human-written examples of how an API can be used. And then the large language model itself is going to annotate a huge language modeling dataset with potential API calls, and then there's going to be a self-supervised loss to determine which one of these API calls actually helped in predicting, in generating better outputs per se. And then the large language model itself is going to fine-tune itself on these API calls that it considered useful. I introduced Toolformer, which is based on GPT-J model with 6.7 billion parameters. And in zero-shot setting, with this kind of setup and pre-training and training and fine-tuning, it outperforms a much larger GPT-3 model with over 170 billion parameters. All right, let's talk more about the approach now. You have a language model M, and you want to teach it to use different tools by the means of API calls. These API calls would require special tokens in order to mark the start and end of each one of the API calls. So if you consider an API call, you can represent it by a tuple like this, meaning that you want to know what API it is going to use, for example, question answering, and what is the input to that API call. And in the case that, so this is that, and let's say you want to get the output. So the resulting output would be R, and you could use this as a special token here as well. So you could see that with or without the output, you could have these types of sequences representing the call to a specific API. Now, one thing that they discuss in the footnote is that in the actual setting, in order to not alter the vocabulary of the large language model, they focus on these sequences. So you have these token sequences, these three. This one is going to be the API tag, this one is going to be the end of API tag, and this one is going to be the outcome. So these sequences of tokens that are specially designed would be used in order not to require altering the vocabulary of the language model. All right, the first and the main thing that they do is that you have a data set which has x1 up until the cardinality of dataset, basically x apps of C. And this is going to be the number of plain text that you have. And the goal is to change and turn this dataset into a C star dataset, which is going to be the dataset now augmented with the API calls. To see this in action, figure 3 is a good starting point. The first thing you have is this important prompt. As this was discussed in the beginning of this video, the goal in this paper, first thing, is to use this generalization ability of large language models by basically providing this prompt. Let's read through the prompt. Your task is to add calls to the question answering API to a piece of text. The questions should help you get information required to complete the text. You can call the API by writing QA question, where question is the question you want to ask. Here are some examples of this API call. And these examples are given because, again, we want to use the generalization ability of LLM to do this few-shot learning task by just providing a couple of examples of how this could actually work. So, for example, Joe Biden was born in Scranton. Here, the LLM is going to learn from this example that you provide that you could put, for example, the question answering API here. And this is another example of that. Note that the goal is that afterwards we want to actually see the API calls in action, basically run them and see whether or not they help the output. All right, so let's go back to the sampling API calls. One thing that is important here is that for each one of the API calls, for example, question answering, search engine, etc., you have a different prompt. X would be the input you're passing to the prompt. And with that prompt, you're going to encourage the language model to annotate these examples with the specific API call that you had in mind. They have brought the prompts in Appendix 8.2. Given this language model M, you have the probability that it generates in the autoregressive fashion for the token n plus 1, given the tokens 1 to n. And what we want to do is that first we want to sample up to k candidate positions for doing API calls. And then what happens is that you take the first I till I minus 1 x's, you also have the prompt, and you want to see what exactly the probability that the model is going to assign to the initiation of an API call. And again, mentioned that this thing was actually represented by its own vocabulary of the language model as the sequence of a space bracket. But anyways, this is going to be the probability that at this point the model would initiate the API call, and this would be PI. Now you want to also have a sampling threshold tau And if pi is larger than this tau s, this is going to be one of the positions that will be kept. And if there are more than k positions, they only sample the top k. Now for each one of these positions, they would consider the sequence px, x1, up all the way until xi minus 1, initiation of an API. This is going to be the prefix. Now the model is going to use this prefix to generate the API with this end of API tag as the end of sequence token. And one technical note that they mention here is that they discard all of the examples for which the model did not generate the end of API token. So far so good. The next step that they have is executing these API calls. For example, if you have an API call to a question answering system or something, you could run a Python script, or you could do a different API call, and for each one of the API calls CI, the output would be a single text sequence RI, and you would get those outputs. Next one has to do with filtering these API calls. In other words, determining which one of the API calls that a model generated using that prompt that you have given it are actually useful API calls. And this usefulness will be defined shortly. So first consider that I is the position of the API call CI in this sequence. So you have a sequence of words x1 all the way to xn. You remember you do have the API as well. So consider that I is the position of the API call, okay? And P of M is essentially the probability, the autoregressive probability of the model, assigning the probability of next token based on it. So if I is the probability of that API call, you have this weighted cross-entropy loss for M over the tokens xi all the way until xn, like this. So you have the W, these are the weights that you want to do, and you start from the position I all the way to n, and you consider the probability of that location xj, the tokens for that location, given the previous ones, and that will be your cross-entropy. Now this would give you a loss. Now what you have here is going to be this. One thing to note here is that when you define LIZ, this Z here is going to be the prefix for your model. So they mentioned in the footnote over here that they define basically input to that loss here as a prefix instead of inserting it to the position I. And the reason for which is that the model that has been pre-trained on the dataset is not yet fine-tuned on any examples that contain these specific API calls. So they don't want to interrupt the flow, they don't want to increase the complexity. That is why they use it as a prefix to the language model. So you have Li plus and you have Li minus. This plus and minus is, you could read it as including the totality of API call and not including, let's say, the result of the API call. So this plus means with the API and its result, and Li minus means either without the API or only with the API and its input, not with its result. And the difference between these two losses is going to give you a quantitative value by which you would measure the usefulness of the API call and its result. In this epsilon is going to be an empty sequence, because in this case you're going to prefix it with the API call and its input, but not its output. Li epsilon means that you're just not getting any sort of prefix pertaining to the API call. And ECIRI is that you both have the API call and its result. They discussed this key component here. They mentioned that you have the weighted loss over all tokens xi all the way to xn here. And what you have is that you want to kind of get the difference between these two components. So let's see this. So the first one is going to be Li minus. It's going to be the minimum of the losses obtained by the first component doing no API call at all, and two, doing an API call but not providing the response. And the other one, Li plus, is the weighted loss over all tokens xi all the way until xn if the API call, meaning the CI, and its result, meaning the RI, are both given as a prefix to the language model M. You could also define this hyperparameter filtering threshold tau f, and you would keep only the API calls for which Li minus minus Li plus is larger than or equal to this tau. In other words, addition of the API and its result compared to the minimum of no API or API without its output decreases the loss by a margin larger than tau f or equal to it. And that would indicate that that API call that the model has generated is actually useful to generating a better output. Alright, now we get to the model fine-tuning. Now, with what we have discussed so far, you were able to generate these meaningful API calls And basically you would generate the API calls for each one of the API types, and then you would filter them out and keep only the useful ones. And now is the time to kind of do the interleaving and fine-tune the model on the sequences, including these API calls. So now you're going to have the corresponding API call CIRI at the position I, and you now have the new sequence X star that you want to work with. And this sequence X star is going to be words 1 to I minus 1, the API call in its result, and the rest of the sequence. When you do this for all the examples in the dataset on which you pre-trained the language model, you're going to have a new dataset called C star. And this C star is going to be augmented with the API calls as discussed before. Now this dataset is going to be used in that procedure to fine-tune the language model M, this time using a standard language modeling objective. Now the idea is that going from passing those API calls in the prefix to essentially including them in the output as well. Now these API calls are going to be inserted in exactly those positions that are needed and those inputs that are going to help the in the generation of the output sequence of words. Now let's talk about inference using that. Now inference and decoding with language model M, which is now after pre-training on the dataset C, is now fine-tuned on C star as well, is that you perform usual decoding until you get the token, the special token right arrow here, which is going to indicate that you would need to run an API call and you would need its response in order to generate the rest of the result. So at this point, the decoding is going to be interrupted, the first part, and then the appropriate API call is going to be called, the response is going to be obtained, and then the decoding is going to start again after inputting both the response of the API call and the special end of API token. And then so basically, when you get to the token this, you know that you have generated an API call and its input. You're going to take those outside of this, let's say, neural network engine. You would run it, let's say, by running a Python script or whatnot, and you would get the output, you would put the output in it, you would close the API call tag, and now with this sequence, you're going to start and continue the decoding. The tools that they discuss in here in order to augment with the language model and overcome its limitations are kind of limited to those that the input can be represented as a text sequence and that the output is a text sequence as well, and those that they can obtain a few demonstrations as well. So they're going to focus on few-shot learning on the input and output being text domain. As mentioned in the abstract, the tools that they have is a question answering system, a Wikipedia search engine, a calculator, a calendar, and a machine translation system. So 1, 2, 3, 4, 5 systems. The question answering system they have is a language model that can answer simple factoid questions, and they used Atlas for this, which is a retrieval augmented LM fine-tuned on natural questions. They have a simple calculator. Then they also have the Wikipedia search, which you provide the search term as its input, and you're going to obtain a short text as its output. Specifically, they used a BM25 retriever for that, which indexes the Wikipedia down from kilt. For the machine translation, they focus on the 600 million parameter NLLB as the multilingual machine translation system that works for 200 languages. They mentioned that inability to nicely deal with low-resource languages is one of the shortcomings of these large language models, and therefore it is expected that including this kind of machine translation system to overcome that limitation and to improve them. The fast text classifier is then used in order to kind of detect the source language to be used for that, and the target language is always set to English. And a final tool that they have is a calendar, which is a calendar API that when queried returns the current date without taking any input. Now let's get to the experimental setup. The dataset C that they want, they use a subset of CCNet from this paper as a language modeling dataset. They use the GPT-J model with 6.7 billion parameters as the model M. They want to reduce the computational cost of annotating C with the API calls, so they define the heuristics to get the subset of C for which the API calls are most likely to be helpful than for an average text. In order to do that, for example, the only texts for which the use of calculator is considered probable are texts that, for example, they have at least 3 numbers in them. When we go over the appendix, the details for these types of heuristics are discussed there. Now, they have the C star from C, then they're going to go based on all of the steps that they discussed in section 2. Then for the weights for the cross entropy, you do remember this JI, so I was the token for the API call, and J was basically set from I to N, and then this would basically mean to W0, W1, all the way to until. So based on this type of normalization, and before this normalization, this type of setup, they have these weights assigned like that. The reason why these weights are set up this way in this decreasing fashion is that they want to make sure the API calls happen in the close proximity to the information that is provided by the API, which is going to help with basically the output being helpful for the model. And then the thresholds tau s and tau f are chosen individually for each tools. And they discuss the heuristics for that in the appendix as well. For the model fine-tuning, they use the batch size of 128, learning rate of 1E-5 with linear warm-up of the first 10% of the training, so you can disavow another detail. The baseline models that they compare against are first GPTJ itself without any sort of fine-tuning, GPTJ plus CC, which is fine-tuned. So this is the GPTJ model, fine-tuned on C. Then the subset of the CCNet that they consider without any API calls is also included in the fine-tuning, so it's called GPTJ plus CC. There's Toolformer model, which is the GPTJ fine-tuned on the C star, and our subset of CCNet augmented with the API calls. This is going to be to the Toolformer. And then another thing is the Toolformer disabled, in which the API calls are disabled during the decoding. What this means is that in that disabled version, you're going to manually set the probability of API token to be 0, therefore masking the option to generate these API calls. And additionally, they also compare with the GPT-3 model as well, which has 175 billion parameters and is used, let's say, in ChatGPT as well. Now let's talk about the downstream tasks. For the downstream tasks, they consider the prompted zero-shot setup. What zero-shot in this context means is that you're not going to provide any sort of, a few examples of how this task is done, let's say with its input and output, and therefore just rely on this description of how to do this task in natural language, which is in contrast to the prior work where models are provided with certain dataset specific examples. And then they focused on the zero-shot task because it is more challenging, and they kind of want to see how their proposed Toolformer works in those cases. There are two key modifications in this practical setup. Is that first of all, they consider a number k and let the model start the API call not just when the next token is most likely, let's say not only when the API token, the special token, is the most likely token generated, but also if it is one of the top k most probable tokens. Before proceeding forward to the next page, let's go over to table 1 and table 2 as well. Table 1 is going to be just several examples of these API calls, so one per each one of the category of API calls. This is the question answering, this is the Wikipedia search, calculator, calendar, and machine translation. And then table 2 is going to be the number of examples with the API call in the C star dataset that they want to have. This is going to be just a number of them, so you do see that there is going to be some certain level of skewness in them as well. And you can see that by increasing this threshold of usefulness, the number of examples that are eligible actually decrease by orders of magnitude. So you go from roughly 1,000 to 138 for a calculator, for example. Anyways, back to this. We were talking about the fact that the model is not just going to focus on the cases in which the most probable token to be generated is API, but in the cases that API is one of the top k most probable tokens, the Toolformer is going to call the API as well. And that means that when k is 1, meaning that when you only generate the API call, when the API token is the most probable one, is going to be just the greedy decoding. And if k is equal to 10, then you kind of increase the disposition of the model to make use of the APIs that it has access to. And at the same time, they don't want to kind of increase this continuation of API calls, so they also manually limit it to one API call per input in order to just see how well it does with one API call. The benchmarks that they evaluate on are Squat, Google RE, TX, and these are the subsets of the Llama benchmark. For each one of these subsets, the task is going to be completing a short statement with a missing fact, for example, a date or a place. The reason for which is the Llama, as a benchmark, was initially designed to evaluate masked language models. They have this slightly more lenient evaluation criterion that the generated token, whether or not it is within the first 5 words that are predicted by the model. So even if the model does not consider the specific token as the top probability, even if it considers of the top 5, it's going to be still is going to be evaluated as correct. Now, Llama was generated based on the statements obtained directly from Wikipedia, so the Wikipedia API call is locked in that case in order to just result in a fair evaluation of the system. This paper showcases the results on the Llama benchmark. You can see that the Toolformer with the API enabled is going to surpass all of the GPTJ-based benchmarks and the Toolformer without the API. And you can see that it even does better than GPT-3 with orders of magnitude larger number of parameters and OPT as well. So yeah, these results are better. For the mathematical reasoning, they focus on ASDiv dataset, SVAMP, and MAWPS benchmarks. So they again set a more lenient evaluation criterion. If the required output is always a number, we simply check for the first number that the model predicts. So they focus on the first number that the model predicts. And if the model prediction generates something like the answer is this plus this equals this, in this case they focus on this kind of character and basically find the first number that is generated after this as the result. And as shown in table 4, Toolformer beats the big models even in this task as well by a large margin. And that resulted in more than doubling the performance across these tasks by allowing the API calls. For the question answering task, they focus on these datasets: web questions, natural questions, and trivia QA. And the evaluation criteria is like this. They consider the first 20 words predicted by the model and try to figure out whether or not this contains the correct answer. This is a more lenient criteria compared to, let's say, exact match. For this, they disable the API call of the question answering because it definitely is unfair advantage, because the underlying QA system that they described that they're using in the system is fine-tuned on natural questions, which is one of the data sets that they are trying to evaluate the system on. So they remove that API, namely the question answering, and they keep the other ones, and then they run the evaluation with that lenient evaluation criteria in mind. As shown in table 5, it still outperforms its other models, but it still lags behind the GPT-3, which is a huge model. They hypothesize that the reason for which are possibly due to the simplicity of the search engine API in this system, the inability of Toolformer to interact with it, or let's say things such as reflection loop and things as such, and they mentioned that this kind of interaction and reforming the query is an exciting direction for the future work. They also evaluated on the baseline models of multilingual question answering. The results on this benchmark are shown in table 6, showing a consistent improvement across all languages. Just here, as you can see, there are languages in which it doesn't outperform, and it's also mentioned here. They mentioned that this reason is probably because of the distribution shift resulting on fine-tuning on the CCNet, which deteriorates the performance. One thing they also discussed is the weak performance of GPT-3 and OPT across these languages, and mostly because they failed to provide an answer in English despite being instructed to do so. They also consider the temporal datasets, namely the temp llama and the new dataset which they call Dateset. The temp llama dataset that they mention is built from Wikidata. It contains queries such as facts that change with time. So for example, Cristiano Ronaldo plays for underline, as well as the correct answer for the years, let's say between 2010 and 2020. Now Dateset, which they describe in the appendix as well, and we will go over it, is generated by a series of templates they mentioned. For example, you could have things such as what day of the week was it 30 days ago, things as such. For this kind of questions, knowing the current date is required, of course, and therefore that API call proves helpful, which is shown empirically as well. They evaluate their models on 2 language modeling datasets as well, Wikitext and a subset of 10,000 randomly selected documents from CCNet. The goal is to show that the performance of the language modeling is not deteriorated after this fine-tuning with the API calls. And they consider the perplexity across all the models in Table 8. They, for example, show that this adding of API calls doesn't come with a cost in terms of perplexity for language modeling, therefore, which is good. Now they do this scaling law section of the paper in which they try to answer the question as varying the size, or in other words, the number of parameters of the large language model, or the language model in this case, how exactly those external tools can be effective. Like they focus on the GPT-2 family of language models with 124 million, 355 million, and 775 million and 1.6 billion parameters. And they only keep the question answering system, the calculator, and the Wikipedia search engine. In this case, they show that a certain threshold in terms of parameter size have to be exceeded in order for the use of these types of external tools to take effect. In figure 4, which we will see shortly, they show that the smaller models, the smaller than this, achieve sort of similar performance both with and without tools, with a certain exception that they explain in here. Now this is figure 4. You could look at it and you can see that for the smallest models here, the impact of using these additional tools is not that much. But as the model size grows, you could see that there are, let's say after a certain threshold of, let's say, 775 million parameters, you can see that they are going to take advantage of these kind of additional tools. And even with the bigger models, this difference in sizes is still, there is going to be a gap between the use of APIs and not using APIs, which is a good thing and shows that this kind of approach is effective. Another interesting part of this paper is talking about the decoding strategy. As discussed before, they consider the K most likely tokens and would make this API call, the model would make this API call if the API token, which is a special token, is considered in one of the K most likely tokens that are supposed to succeed that text. Now, if that K is 1, it's going to be the same as greedy decoding. If it's 0, you don't generate or make API calls. And if K, for example, goes up to 3, 10, that means more lenient API calls being made, meaning that the number of examples on which the model would decide to make an API call would increase. This was also shown in table 9, in which they run it on WebQS and also in the T-Rex subset of Llama benchmark. As you can see, the value of K is increasing, 0, 1, 3, 10. You can see, for example, in WebQS. Here you see the percentages of the performance. The all indicates all of examples. AC is the examples on which the model decided to do the API calls. And NC is basically the remaining examples. And this percent here is the percentage of examples in this data set on which the model decided to make an API call. You can see, for example, on WebQS, as you go from the values of K from 0 to 10, you can see the number of the examples on which you generate or make the API calls go from 0 to 100% of them. Same goes with the T-Rex. You could see that overall, for example, there is improvement here. And you could see that even for a K of 1 in the greedy coding, there is a clear improvement in the WebQS dataset as well. All in all, this table shows the importance of these API calls as well. They also do a qualitative review of these API calls and to what extent they ended up being helpful. So on the right here, you see this this margin here shows the usefulness of these things. So if here, for example, you could see one with this large margin, meaning that it is most probably useful. And if you read the example, you could see that the positioning of the API call is pretty interesting. And then as you go down, you could see some of the not very useful examples as well. Like, for example, the not very useful use of calendar API to get the date. All in all, this kind of qualitative review of how useful they are, in addition to this quantitative measure, is an interesting way to look at this problem. In discussing the limitations of this work, one limitation that they mention is the inability of the Toolformer in using tools in chain, or in other words, as they define it, using the output of one tool as an input for another tool. Another limitation that they remark upon has to do with their setup, in which they do not allow the model to use these APIs in an interactive fashion. They also mention the sensitivity of the models trained with Toolformer to the exact wordings of their inputs in making a decision of whether or not to call the API. In the appendix, they talk about the API details. They give the values for TOS and TOF, and things such as limitations that they set on the model, for example, the at least 5% probability of API only kind of detecting the kind of being a necessary condition to make the API calls. They only keep top K equals 5, sample up to 5 API calls for each position, and more details on this front. They also provide more details on the implementations of these components of the work. Now let's go and talk about the prompts and see those prompts. Here they mention the prompts for the different components of this work. Feel free to pause the video and look and read each one of these prompts. The first one is the question answering prompt, the calculator prompt, which continues here, the Wikipedia search, the machine translation, and the calendar, with more examples here. Alright, for training the Toolformer, they have 25,000 examples per API. The max sequence length is going to be 1024, effective byte size 128. The models are trained using DeepSpeed 03. They used 8 NVIDIA A100 40GB GPUs with the BF of 16. And then they trained them up to 2,000 steps, and they evaluated PPL on a small development set of 1,000 examples. So this is, sorry, I'm just reading through this. This is just like the descriptions of this Toolformer training. Now the interesting part are these zero-shot prompts. For example, you could see this one for the temp lambda, asking the language model to complete the text so that it is factually correct. The math benchmark is that the answer is, question answering is the answer to the following question. Multilingual question answering is, you get the picture. These are details of the patterns of the prompts that they used in this setup. In table 11, they go over the templates and the sizes by which they basically designed this as a protocol for creating their dataset, which they call Dateset. And you could see it here. By the way, I think I called this by mistake Dataset as I was reading one of the earlier pages. Sorry, so its name was Dateset. And this concludes our discussion in this video. Thank you so much for watching, and I hope you found it useful.